So what exactly are groups? Let me begin by giving you a brief introduction to this concept. And it's a concept that's intrinsically linked to that of symmetries. So I want to begin by asking you some motivating questions related to symmetries. In particular, which of these shapes that I'm about to draw is more symmetrical? For whatever more symmetrical might mean to you. Okay, so my two shapes are a triangle with just some arbitrary angles and what's supposed to be an equilateral triangle. Okay, so I think we can all agree that for whatever definition of symmetry we're going to use, the equilateral triangle is going to be considered more symmetric. Okay, what about the following two shapes? I'm going to now draw a rectangle and a square. Okay, and again, I think there's something inside us, some kind of intuition that tells us that it's the square that's the more symmetric shape. Okay, so going to see why that might be. So first of all, what do we mean by symmetry? Well, by symmetry of an object, we mean something that we can do to it that actually preserves how the object looks. Okay, that preserves its structure and leaves it looking the same. Okay, so in the example of one of these shapes, the kind of things we might be looking at are reflections and rotations. Okay, so we can do a reflection. Let's take our equilateral triangle. I'm just going to label the vertices so that we can see what we're doing. And I'm going to perform a reflection in this axis here. So what that will give me is a shape that looks exactly the same. And we see that we've just reversed B and C here. Okay, we can also do a rotation. Let's, for example, do a clockwise rotation by an angle of 2 pi over 3. Okay, so what will that give us? Well, if I take again my shape, if I do my rotation, then what I'm going to get is, again, a shape that looks exactly the same with the following labels of vertices. Okay, so now that we know what we're talking about when we're talking about symmetries, we can actually count how many symmetries each of these shapes above has, right? So the first shape, this non-equilateral triangle, what can we do to it? Well, because of the way its angles are, we can't actually do any rotations or reflections to it, but we can do one thing, and that's not do anything, okay? And in maths, we will count that as an actual thing that we can do to it. Okay, so the do nothing symmetry, if you like. Okay, so this one only has one symmetry, the do nothing symmetry, okay, or the identity symmetry. Okay, what about the equilateral triangle? Well, we're going to list all of its symmetries in a second, and we'll see that there are 6 of them. Okay, the rectangle now, so we have the do nothing symmetry, we have the reflection in this axis, the reflection in this axis, and also the rotation by pi. So we have 4 symmetries altogether, and we can do the same thing for the square, and we also gain the reflections in the diagonals, and so that gives us 8 symmetries altogether. Okay, so you can see that our intuition was right, and the shapes on the right hand side are more symmetric, just in that they have more symmetries. Okay, let's explore further. So for our equilateral triangle, let's list all of the different symmetries that we actually have. So what are all possible symmetries? Okay, so, well, we have, first of all, as we said, the do-nothing symmetry. Then we have the reflection in this axis here. Then we have our rotation that we already mentioned. Okay, we can do that rotation again to the triangle to get this triangle here. Okay, and then what else do we have left? Well, we also have the reflections in the other axes. So this is the reflection in this axis here. And finally, the reflection in this axis will give us this labeling here. Okay, so we can see that altogether there are in total 6 symmetries of the equilateral triangle. Okay, you can check that there really are no other ones. And something to note is that, okay, so first of all, we've included this do-nothing symmetry, as we already mentioned. So note we've included the do-nothing symmetry. Another thing to note is that we have a way of reversing each of these symmetries using another symmetry. So we have a way of undoing or reversing each symmetry. So just to give you an example, in the example of our reflection here, we can do this reflection, but then we can just do the same reflection again, and what we'll get back is the original triangle. Okay, so we have a way of reversing that symmetry using another symmetry. And for our rotation here, what we can do is simply do a rotation anti-clockwise by 2 pi over 3. That's also a valid symmetry of our equilateral triangle, and this symmetry will reverse or undo the rotation that we've already done. Okay, another very important feature of symmetries is that if we do 2 symmetries in a row, we actually perform another symmetry. So the composition of 2 symmetries gives another symmetry. So note also that doing 2 symmetries in a row makes another symmetry. Okay, just to give you a concrete example of that, so again with our equilateral triangle, so I'm first of all going to do, say, the reflection. Maybe let's give the reflections and rotations names. So I'm going to call this reflection S, and I'm going to call this rotation R. Okay, and the do-nothing symmetry, I'll always refer to it as E in this course. Okay, so I can first of all do my reflection. That will give me the following, and then I can follow that up with my rotation, and what I'll get is this. Okay, and you can see that this symmetry it actually is one of the symmetries already on my list. Okay, it's right here. Okay, so indeed by doing 2 symmetries in a row, I do already get I do get a symmetry that I already had. Okay, another valid symmetry of my shape. And so the way I'm going to write this composition of S and R, I'm going to write it as R times S. Okay, and the reason I'm writing it in that order, even though I did S first followed by R, is because I'd like to think of this these symmetries as being applied as a function to my triangle. Okay, so that's why S comes on the right here, because it's the first thing that I'm applying to the triangle. Okay, so that's the reason for this notation. Okay, just out of interest, let's see what would happen if we did R first and then we followed it up by S. Okay, so what would happen then? So if I do R first, I get this, And if I now do my reflection in this axis, right, what will I get? I'll get this. Okay, and so that's my element SR. And so what I can notice is actually, again, so this is a symmetry that's already on my list. It's right here at the end. Okay. But what I notice is that actually the order matters. So RS is not equal to SR. Okay, so that's important to note, that sometimes the order in which I do symmetries matters. So in fact, it's not only the number of symmetries that's important for a given object. In order to really get to grips with what these symmetries are, we also need to study the relationships between the different symmetries. So we can investigate the relations between the different symmetries, or elements, if you like. Let's write symmetries. Okay, and just to give you an example, so I'm going to draw a shape that also has 6 symmetries, just like the equilateral triangle we just looked at, but these symmetries are going to behave rather differently to the ones we just saw. So, so the following shape also has 6 symmetries. Okay, and so this shape is going to look as follows. So I'm going to first of all attempt to draw a nice, neat, regular hexagon. Okay, then I'm going to draw in the diagonals, and then just draw in these segments as well. Okay, so I've divided this shape into 12 parts, and I'm going to color some of these parts in. Okay, so I'm going to color in every other segment. Okay, pretend this is a nice, neat coloring of these segments. So coloring in every other segment like so. And then what I'm interested in is symmetries of this object that preserve not just the shape, but also the colors. Okay, so if you notice, this shape now doesn't have any reflections, right? I can no longer just pick a line, let's say this line, and reflect in it, because that would reverse the coloring, and that's no good. Okay, so there are no reflections, and so we only have rotations, and there are 6 of them, okay, including the do-nothing rotation, if you like. So, so we have 6 symmetries, just as for the equilateral triangle, but they behave very differently to those above. So these symmetries behave differently to those of the equilateral triangle. So one thing to spot is that the order in which I do the symmetries will no longer matter. Okay, you can check that no matter what order you do the different rotations that we have for this shape, you're going to get the same answer. Okay, whereas that wasn't the case above, as we just saw. Another thing to notice is that so if we, for example, pick the rotation by 2 pi over 6, okay, so repeating the rotation by 2 pi over 6, if we repeat it less than 6 times, this will never get us back to the original position. Okay, so this rotation, this is kind of the smallest rotation, smallest non-trivial rotation that we can do. If we repeat it less than 6 times, we're not getting back to the original position. Whereas for the triangle, if we think about all of the symmetries that we looked at above, actually repeating any of them 2 or 3 times is sufficient to get us back to the original labeled shape, right? So that's another difference between these two sets of symmetries. Let's write that down. So whereas for the triangle above, any symmetry can be repeated 2 or 3 times. Okay, if it's in particular, if it's a reflection, we can repeat it 2 times. If it's a rotation, we can repeat it 3 times to get back to the original. Okay, so what this means is that it's important not to study only the number of symmetries of an object, but also how they actually interact. Okay. Study the symmetries of an object. We need to study how they interact. So we actually need some additional structure on the set of symmetries. And that's exactly where groups come in. So groups are an attempt to give an algebraic structure to the set of symmetries so that we can better understand this set. Okay, so now what are groups? So groups are sets of elements, or you can think of them as symmetries, just as above. Importantly, together with rules on how to compose them. So this captures this idea that it's not just the set that's interesting to us, but it's also how the elements of the set actually interact. So something to notice that groups will always contain the do-nothing element or symmetry. So we always need to have that in there. So this is called the identity element or symmetry, just as for our symmetries that we looked at above. Something important that we mentioned is that composing two elements of a group should give us another element in our group. This gives us another element in the set that we have, the group. Something else that we already spotted is that for each element, we must have another element in our group that is able to reverse it. Okay, so for each element, we have something called an inverse for that element, a way to undo it. And finally, so there's another rule that we need for composing elements in a group, and this might seem a little bit abstract. So if I write, suppose I had two elements in my group A and B, I'm going to write A star B for the composition of A and B. Okay, just for the purposes of explaining this. So another rule that elements in a group need to satisfy is the following rather abstract looking thing. So I want to be able to say that if I compose A and B first of all, and then I compose the result with C, that needs to give me the same result as the composition of A with the composition of B and C. Okay, this is a rule called associativity. We'll see in the course why this is important. It might appear very abstract, or it might appear almost sort of trivially true. You might struggle to think of objects that, sets of symmetries that don't satisfy this rule. But actually, when we're studying groups more generally and the symmetries are disguised as maybe other operations, this rule really is crucial to verify in order for our object to be a group. Okay. And so the interesting thing is that we can now actually forget, once we have our set of symmetries or set of elements in our group and a way to compose them that satisfies these rules, we can actually forget that these were symmetries and just look at the set of elements with this set of rules. So we could now just forget that these were symmetries and just look at them abstractly as elements with certain rules for composing them. So that's really the power of abstraction here. We can study groups just for their own sake, but often it is useful to remember that the elements actually came from a context of symmetry, and we'll see in the course that sometimes this context is very important and actually gives us additional information.
Now you might be wondering, why did we choose this particular set of rules for our compositions to satisfy? Okay, well, we could have actually chosen a completely different set of rules. For example, we maybe could have asked that the order of the composition doesn't matter, but this would have made a different object for us to study. Okay, and actually in maths, algebra is the area of maths that studies the kinds of objects that we can create by imposing different rules on how to compose elements of a set. Okay, so we can make many interesting things for us to study. But I do think there's a case to be made for groups being one of the kind of most beautiful objects in algebra, simply because they find themselves somehow in the middle between having too many rules and not enough rules. Okay, so imagine a game or a sport where there are just too many rules. Okay, you can't actually make any progress in the game without the referee blowing his whistle and telling you you're doing something wrong. Okay, that's not going to be a very fun game. You're not going to actually be able to do anything in that game. And then equally, if there are no rules at all, then you might think you're playing football, but then somebody could come at you with an axe or something. So that would be just total chaos and not very fun either. So groups, for me, they really find themselves in that perfect middle ground between not enough rules and too many rules. So when you impose too many rules on an algebraic object, you get something very rigid, something maybe you can say a lot about, but something that won't be very interesting. You probably don't have very many interesting open questions about that object. Okay. On the other hand, if you don't impose any rules, then your object can be pretty much anything. So it's very hard to study it when it just doesn't have any structure at all, right? So groups, I think, are very beautiful for that reason, and also because they do happen to satisfy the rules that real life symmetries satisfy, like the symmetries of the shape that we've just seen.